So now let's have some fun with these raising and lowering operators. So suppose you want to calculate the expectation value of the position cubed making a transition between the energy state 2 to the energy state 3. So, I'm not exactly sure why, but it will illustrate exactly what we can do with these raising and lowering operators. So if we want to find this expectation value with the wave function, then what you would have to do is calculate that integral for the expectation value. So I would integrate from minus infinity to infinity, and I would take the wave function for the third energy state, complex conjugate, operate with x cubed on the energy, the wave function of the state n equal 2, and then integrate. So if we add in now the wave functions that we have, then what we would get is, and you have to bear with me, the mass times the frequency, pi h bar 2 to the 6th power, because it's 2 to the power 2n, 3 factorial squared, all of that to the 1/4 power, e to the minus m omega x squared over 2 h bar, the Hermite polynomial for n equal 3, m omega over h bar square root times x, operate with the operator x cubed, and then repeat for the wave function where n equals 2, m omega over pi h bar 2 to the 4, 2 factorial squared, all of that to the 1/4 power, e to the minus m omega x squared over 2 h bar, Hermite polynomial 2, with the argument the square root of m omega over h bar x, integrated over x, so there's a dx in there. So we could clean it up slightly, and we would have the integral of m omega over pi h bar square root 1/2 8 times 6 times 4 times 2 to the square root e to the minus m omega x squared over h bar x cubed, Hermite polynomial 3, Hermite polynomial 2, dx. All that put together. So while this integral looks fun, and we could just plug in the value, the terms for their Hermite polynomials, multiply them out, look up in the integral table all of the integrals for each of those terms. Let's try it with raising and lowering operators. Okay, so the raising and lowering operators, that would be h bar over 2m omega square root a plus a dagger, the whole thing cubed, operating on the state n equals 2. Okay. So let's pull the non-operators out front. So that's h bar to the 3/2 power over 2m omega, I guess also to the 3/2 power. So let me just clean that up. So this whole thing to the 3/2 power, 3 operator a plus a dagger cubed, operating on the state n equals 2. Okay, so now let's expand that out with the binomial. So I have a cubed plus a squared, a dagger, plus a dagger, a, plus a dagger, plus a dagger, a, plus a dagger, a dagger, plus a dagger, a, plus a dagger cubed. So all of that is going to operate on the state n equals 2. So we can't combine terms because of a commutation relation. So we could actually try and clean this up with a commutation relation, but instead, why don't we just try and do it term by term? So if I took a cubed operating on 2, that would be the same thing as a operating on 2, which would be a square root of 2. Now I've lowered it to state 1. Square root of 2, square root of 1, a operating on the ground state, which would basically be 0. You can't get anything lower than the ground state. Okay, so now let's try the next one. A dagger operating on the state 2, a dagger operating on the state 2. So this is the first term. This is the second term. A dagger operating on state 2 raises it to state 3. So I get the square root of 3, a, now the square root of 3. And I lower this 3, so I get the square root of 3 times the square root of 3, a on the square root of 2, which is the square root of 3, square root of 3, square root of 2, and the state 1. Okay, so let's go on to the next term, and that is a dagger, a operating on 2. So lowering 2 would give me a square root of 2, state 1. Raising 1 back up to 2 would give me a square root of 2. And I'm back to the state n equal 2. Lowering that back down to 1, I would get now square root of 2, square root of 2, and another square root of 2, back to the state 1. Okay. I4. So the fourth term is a dagger, square root of 2. So that raises it to the third state. That raises it up to the fourth state. And then a lowers it back to the third state. So we get the square root of 3, square root of 4, square root of 4 to the third state. So at this point, what I should be aware of is the fact that we're eventually going to make a product with the state 3. And so if I look at, say, the second term, a dagger on 2 is the third state. That one was 3 times the square root of 2, now in the 1 state. But because of orthogonality, I can't make the product of a 3 and a 1. So therefore, I can eliminate this second term because it's going to give me an orthogonality of 0. I can eliminate the third term for the same reason. And so then, the fourth term now, I'm going to take state 3, a dagger, state 2, which I said was 3, 4 square root of 3 back to 3, 4 square root of 3, 3 projected on 3, which gives me a 1. And so this is now equal to 4 times the square root of 3. So basically, I'm only going to keep terms that are going to give me, I'm going to end up in the n equals 3 state. Because when I project it onto the n equals 3 state, I get a 1. If it's any other state, orthogonality says that product is going to be equal to 0. Okay, so now if I look at my other states, the fifth term was A dagger A operating on the second state. So that would give me square root of 2, A dagger A, drop down to 1. Square root of 2, square root of 1, A dagger on the ground state. I raise it up to the first excited state. So I get the square root of 2, square root of 1 on 1, but the projection of 3 on 1 is going to give me a 0. So I can eliminate this one. So that one is not going to contribute. Okay, so let's look at the sixth term. The sixth term is A dagger A dagger operating on 2. So let's see, so A dagger is going to raise it up to 3. So that's going to raise it up to 3. Now, A on that is going to lower it down to 2. And A dagger is going to raise it up to 3. So this one is going to work. So I shouldn't have stopped there. I should have just worked it out. So A dagger A dagger state number 2 gives me square root of 3, A dagger A on the third state, square root of 3, square root of 3, A dagger on the second state, and then raising it back up, I get the square root of 3, square root of 3, square root of 3 on the third state. So I get a 3 times the square root of 3 on the left with the third energy level. So this one's a keeper. Okay, so I get 2 more terms. So the seventh term is A dagger A operating on 2. So this one is going to lower it down to 1. But then A dagger is going to raise it up to a 2. And then A dagger is going to raise that one up to 3. So I'm left with 2 square root of 3 on the state 3. So that one's a keeper too. And lastly, the eighth term was A dagger operating on 2. And this one is going to raise it up to 3. The next term will raise it up to 4. And then the last term is going to raise it up to 5. So this one, I'm not even going to calculate. That one I'm not going to keep. So in the end, the terms that we keep are going to be term number 7, term number 6, and term number 4. Okay, so in the next video what I'll do is I will pull this all together.